Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to learn about how to design built-up compression members according to CSA O86 14, which is the Canadian wood design standard. Okay, so built-up compression members, basically I take multiple pieces of wood and put them together so that I can get a stronger column, okay, or stronger compression member. It doesn't have to be a column. As long as I'm talking about loading in compression parallel to grain, then I can design built-up columns. So here, if I had two 2x4s, for example, and I put them together using nails or bolts or split ring connectors, then I can consider this as being one solid column. And if I do that, obviously I'm going to get a big bonus to my buckling strength, compared to if I had to consider these as two separate columns buckling and just happening to be next to each other. I do have to apply a reduction to the strength to account for the fact that we cannot connect these together perfectly using nails or bolts, but we still get a huge benefit to sticking them together, and we're going to see why in this video. And in the standard, it says that you can put up to 5 members together to make a built-up section. And this applies to lumber and to glulam, and the same requirements apply to both. So everything in this video is both for lumber and glulam, but it's much more common to see this kind of thing with lumber, because lumber members are smaller to start with, so it makes more sense to stick them together to make a bigger member. Okay, so let's look at what one of these built-up columns might look like, and what are the requirements if I want to build one. So here's a built-up column member. This one is very short, just that it fits on the page. Generally, you would be talking about something longer because slenderness is probably your concern when you're doing a built-up column or built-up compression member. Here I have 3 different pieces of wood, probably lumber in this case, but could be glulam, all stuck together. So instead of 2, I have 3. And as I shown there, they are either nailed or bolted together. And you can see I've just indicated some nails here. This one, since it's 3, you could call that a 3-ply built-up column. Okay, but that just means that it has 3 members, and I can go up to 5. So here are the requirements that we have to meet for if we want to design a built-up column. So first is there's a requirement on the thickness of the plies. So each individual ply of the built-up column has to be at least 38 millimeters thick. So that means a 2-by member is the minimum member that that I can use. Anything bigger than that is fine. 2-by, 3-by, 4-by, all of those are fine. They do not all have to be the same thickness, but again, the minimum thickness is 38. We can have somewhere between 2 plies to 5 plies for a built-up column. The standard does not allow for more than 5 ply. There's 3 different options given in the standard for built-up members, for how to connect them together. We can either use nails, bolts, or split ring connectors. We are going to discuss nails and bolts in this course, but split ring connectors are not included, but you can look for yourself in the standard for what split ring connectors are and how to design them. Also, we have to meet the minimum spacing requirements from the standard for nailed connections, which is obvious. So basically the nailed connection has to be a legitimate nailed connection according to the clauses of the standard. We're not allowed to do glue explicitly for that, but you might, in order to put the plies together, although you might recognize that if we did glue these members together, and if we glued it properly, then effectively what we would have is a glulam column. So glulam is kind of like a special case of a built-up member, and we treat it separately. So if we do meet those bolting and nailing requirements when we make our built-up section, and there are some additional requirements for those that we're going to talk about for exactly how many rows you need and how to space out the bolts and nails, which we'll talk about in a minute. But if I meet all of those requirements, then I can treat my built-up section as if it was an equivalent solid section. So if this is a 38 by 38, 38 by 89 and a 38 by 89, and I put them together, then basically if I follow the requirements of the standard and nail these together properly, then the size of this becomes a solid section that is now, instead of 38 by 89, it is 76, right? 76 by 89. And that becomes my new section. Then I consider as if that's a single piece of lumber, with the proviso that to account for the fact that they're nailed together, I have to reduce the overall strength of that section to 60% of the total for nailed connections and 75% of the total for bolted connections. And you might say, well, I mean, yeah, I've made the section bigger, but now I have to reduce the strength. So what's the benefit? Turns out there's a really big benefit because of how the slenderness factor is calculated. So if I look at our equation for slenderness factor, and this equation applies both to lumber and to glulam, as you'll recall, for regular compression parallel design, we have CC, which is our slenderness, and you can see that this thing is to the power of 3. So we cube our CC, right? CC is cubed in this equation. Okay, and this is a reflection of the fact that our second moment of area, or commonly called moment of inertia, I, for a rectangular section is BH cubed over 12. Right, so as I increase the height of the section, my moment of inertia goes up by a factor of 3, right? By a power of 3, sorry. So it makes a really big difference. So even if I'm reducing the strength by 40% for nailed connections, I'm increasing my buckling strength, you know, on the order of a power of 3, because my I is increasing by a power of 3. And here CC, you know, all this stuff is a stand-in basically for I in this equation for KC. So as I change my slenderness by a little bit, it has a much bigger effect on the strength. And so as I increase CC, like if I were to increase my slenderness, then the problem gets worse very fast, right? And since this is a -1 on this equation, like it's an inverse, once I do the whole thing, as my CC increases, of course, my KC decreases, and it decreases fast. And then so if I'm looking at it in the other direction, if I'm decreasing CC, then I get the same benefit, but in the other direction. So it very quickly decreases the effect of slenderness as I reduce my slenderness. So that is the big benefit of putting these together. So let's look at that a little bit more closely. I'm going to draw again what this built-up member looks like so that we have some basis for our comparison. So here's my 3-ply section again, just looking at the top of it so we can see how the plies are put together. So this one's 3-ply. We have H, which is the strong axis direction of the individual pieces, and I've labeled B1 here as the thickness of one of the plies. This is not a variable that's from the standard, but just one that I'm defining based on an individual ply thickness so that we have something to talk about down below. And L, the big L, that's the total length of the built-up member, which we're not seeing the bottom of. So let's compare what would happen if I consider these 3 members to be just individual members stacked up against each other. So as if I'm just calculating, I calculate the strength of one, I calculate the strength of another, and I calculate the strength of another, and I take those total strengths and I add them all up to get the total strength of the member. That would be if I am not doing a built-up section. Compared to what is the strength of this if it is a built-up section, which means that I've connected them together well enough that I can consider the whole thing as one solid member. So let's see how the calculations differ between those two cases. Okay, so if I'm just comparing the calculation of the slenderness factors, C, and in the code it just says, or it should be CC. Yeah, sorry, CC strong, CC weak, CC strong, CC weak. So if I'm just comparing the slenderness factor CC in the strong and weak directions, if I do it individually or if I do it built up, let's see what I get. So for C strong, that's the slenderness for buckling in the strong direction, I need to find first my effective length, which depends on the unrestrained length, right? The length between places where my section is restrained against buckling. And also the K, which is my the factor according for the boundary conditions of the member. And we divide that by H, which is the length of the cross section in the direction of buckling. So if I have strong axis buckling up here, we're talking about buckling in this direction, right, in the red direction, and H is my relevant parameter, and L, we've looked at how to calculate that before, so that doesn't change for built-up sections. Once I have a built-up section, my CC strong, is still going to be the same. I have LE, and I still have H, because remember, the benefit of the built-up section is that I get to treat this as one solid section, and that solid section, if I have these two pieces again, okay, okay, so when I had this individually, the strong axis direction was this, 89, right? The 4 of the 2x4. If I put them together, okay, and now I'm considering this as one section, what's the strong axis direction length? It's still the same. It's still 89, so it hasn't changed. Okay, whereas for the weak axis direction, I still have my LE for weak axis buckling. Okay, so those LEs might not be the same. These can differ, right? Can differ based on boundary conditions and how it's restrained, right? But for how I calculate the slenderness, right, if I'm looking at these individually, obviously my slenderness for each of them is going to have this weak axis direction dimension, right, which is the 38, right? So I'm going to have 38 for this one and 38 for this one. So again, I'm considering these two as separate in the left, and each one has a slenderness that's defined by its short axis, its weak axis dimension of the cross section, this one 38. But now when I put these together, I can actually consider the full section as one, right? So now I have I have 2 plies here, so this is going to be 2 times B, right? So it's going to be 76 instead of 38. And in the example that we're doing on the sheet here, it's 3 times because there's 3 plies, right? This is because of 3 plies. Oops. This is 3 ply. Okay, so for more than 3 plies, this number would change. Okay. So that's a big difference, right? So I'm going to have 1/3 of the slenderness as I did before when I did the original built-up section, right? And so remember, that doesn't account for 1/3 of the strength. So if I go from the right side to the left side, that doesn't mean I have just 1/3 of the strength. It means much more than that, because slenderness is raised to the power of 3, as you remember. So it's much more than 1/3 of the strength. It's not quite an 1/8, but or it would be like a 27th. It's not that bad, because that equation is not directly proportional to slenderness, the KC equation, but it does make a huge difference. Okay, so what you want to take away from this is that the weak axis changes a lot, but the strong axis, these ones are the same. So strong axis slenderness when we do a built-up section doesn't change. But the weak axis slenderness changes a lot. Okay, so let's continue and look at what's the next step usually is that we calculate KC for both directions. So when I go to calculate KC, on the left side before I have it built up, I'm calculating KC for each individual member based on CC of the same on the left. So KC strong is going to be using CC strong in that equation. I'm talking about this equation right here. This is the KC equation. So I have to plug a CC in here, which is my slenderness. So for KC strong, when I'm doing it individually, I'm going to use CC strong. For KC weak, I'm going to use CC weak based on the slenderness of the individual members, which is the one that's just above there on the left. This one here. On the right side, KC strong, I'm going to use CC strong. That CC strong is the same. So it's the same strong axis slenderness as on the left and the same one as above. And KC weak, I'm going to use CC weak, but this time it's the built up version of that. Right? So that's going to be a much higher KC in the case on the right, right? Because KC is the factor that accounts for slenderness. So higher KC factor means less slenderness effect. Lower KC factor means more because I have to reduce my strength by more. Now I take that KC and I plug it into my equation and I do it like this. Okay, so on the left, if I'm considering each of these to be individual, I'm going to do two calculations for lumber, right? One is PR strong and one is PR for weak axis buckling. And the PR strong is exactly what we're used to. I have phi times FC times A. Oh, this should be 3 times as well. I'll get rid of this here too. It's the same. Okay, and this A here is of the individual member. Right, so each individual ply has an A, and that's the A I use in there. And then I'm going to multiply it by 3, right? Now here on PR weak, I'm also going to have 3 different members, and this is still also the individual member. And I'm going to multiply that by KC weak, right, which is going to be quite small in this case because it's the KC weak associated with just one member buckling, not the whole section buckling together. Then on the right, once I consider that it's a built-up section, right, then I have for PR strong, phi FC A KZC KC strong. But now this A is the total A, right? Which equals 3 times A individual, right? So these equations here are identical. The PR strong for if I'm doing it as 3 separate members, or the PR strong if I'm doing it as a built-up complete member altogether, I'm going to have the same strength. Either I multiply by 3 before I do the equation because I'm counting each individual member, or I'm multiplying the area by 3 because now I'm considering the built-up section altogether. Right? Now for PR weak, I have phi FC A KZC KC weak. Same thing, right? Except my KC weak is different than the KC weak than I used on the left. And the and this is the same A. I wonder if I can do that a bit better. So these are both the total A of the cross section. So that would be, if I consider this built up section to be one solid member, it's this whole A here, okay, which is 3 times the A of the individual section. And then I multiply that by 0.6 if I'm using a nailed connection to put my built-up sections together, or 0.75 if I'm using a bolted connection. So it looks like the difference between these two is that the one on the right should be less because I have a nailed or bolted modifier here for 0.6 or 0.75. But that's not the case because the KC weak between the two, this one here in orange and this one here, these are very different, right? Because one is calculated using the individual slenderness, which would be very high slenderness, giving a very low KC. And the one on the right is calculating using a much lower slenderness, which is going to give a much higher strength. So these are very different. Whereas the KC strongs were the same. Okay, so basically this whole built up section, it doesn't affect the strong axis buckling strength at all. And that's what you should take out of this. And it does affect the weak axis buckling strength. And even though I have to reduce the strength to 60% or 75%, the change in KC more than makes up for that. Like it makes up for it in spades generally. So I'm going to get a big benefit by considering it as a built up section. Let me just summarize that part about the strong axis direction. The built-up section does not affect the strong axis buckling strength. Okay, so the very last thing that we need to cover then is what are the requirements for built-up sections when I nail them or when I bolt them. So I have the requirements already from above that I have to have a 38 millimeter minimum ply thickness. I can do 2 to 5 plies on my built-up section, and I have to make sure that my section is connected adequately by nails, bolts, or split ring connectors. So we have to say, okay, what is it that, how do I define that it's connected adequately? Well, the standard provides explicit direction for what constitutes adequate connection between the plies. And I will call out the clauses as well. So we're going to start with the nailed built-up section requirements. So again, if I follow these requirements, then it allows me to achieve a maximum 60% of PR weak for an equivalent solid section. So considering that my built-up section is actually just one big piece of wood that doesn't have plies. Okay, so there's 3 requirements here. So the first requirements have to do with how these nails are spaced. So if I'm nailing into the section, I'm going to have spacing between those nails. And those spacings are defined by what is the thickness of the thinnest ply. So that's why I'm saying B min. So imagine I have 3 plies here. They could be all different sizes. Whichever one is the thinnest one, that defines what my spacing requirement is. And so you can see that spacing along the length of the member has to be less than or equal to 6 times that thickness. And spacing between rows, if I need more than 1 row of fasteners, is 20 times DF. And DF is the nail diameter. We're going to see this parameter a lot when we start talking about nailed connections in detail. And B min, again, is the thickness of the thinnest ply. Okay, so the second requirement now. So requirement B actually has 2 requirements, and they have to do with how the nails are actually laid out and go into the members. So one requirement is that the nails have to alternate in direction. Nails alternate. So if I have one nail, the next nail, if I have one nail that goes in one side of the member, the next nail down has to go in the other way, and then the next nail below that has to go in the other way, and then the next nail before that has to go in the other way, and so they have to alternate directions. The second requirement is on the length of the nails. So I have to choose nails that are long enough so that they will penetrate at least 3/4 of the way through the last ply at the tip. So you can see the first nail at the top goes all the way through the first one, all the way through the second one, and it goes into the third one, and it has to go at least 3/4 of the way into the third one. It could be more than that. You could poke it through and bend it up on the other side, although that won't look very pretty, but that's the requirement. So I have to make sure that my nails are long enough so that I'm actually connecting these plies together properly. Now the third requirement. The third requirement has to do with whether you need to have 1 row of bolts or 3 rows of bolts. Wow, that is a pretty crooked piece of wood that I drew there. Anyway, I hope that that's charming. So on the left side, I'm showing kind of 2 pieces of wood that are not very wide compared to how thick they are. And on the right side, I'm showing individual plies which are a bit wider. They have a higher aspect ratio. So the border line for that is if H over B1 here, so where B1 is 1 ply thickness, is less than 3. So if the length is less than 3 times the thickness of the piece, or if I show the piece, if the length of this piece is less than 3 times the thickness, which it is for 2x4, right? Because this is somewhere on the order of twice this, right? A little bit, well, no, actually it's about 3 times, because this is 1.5 and this is 3. So if I have a 2x4 or chunkier than a 2x4, then I'm allowed to have only 1 row. 1 row is okay. If H over B1 is greater than 3, which looks like what I've shown on the left, actually, sorry, left side is less than or equal to 3. If it's greater than 3, then we need at least 2 rows of nails. And how those rows are spaced from each other was a requirement that we discussed already previously, which was up here, right? So that's how the row spacing works. Okay, so as long as you satisfy those 3 requirements, the requirement for nail spacing, the requirement for penetration of the nails and alternating direction, and the requirement for whether you need 1 or 2 or more rows of bolts, if you satisfy all 3 of those, then you have considered an adequately connected nailed built-up section, and you can calculate the strength of that section for the weak axis buckling using 60% of the strength that you would get if you considered it to be a solid full section. You know, as if it was just one big piece. Okay, so let's look at the requirements now finally for bolted built-up sections. Okay, so if I can satisfy these bolted built-up section requirements, the connection requirements for making a built-up section out of bolts, I will be permitted to consider the section strength as being 75% of the weak axis buckling strength for a solid section the same size as the built-up section. The first requirement, which is just in the body of the clause, is that you need to use 1/4 inch diameter bolts at least when you put these together, so you can't use a smaller bolt than that. And then we have basically 2 requirements for bolted sections. So here is the first one. Okay, so this first requirement is a spacing requirement, which is very similar to the spacing requirement that was there for nails. So basically, we again look at the thickness of the thinnest ply, and the nailing spacing, sorry, the bolt spacing along the length of the member needs to be less than 6 times the thickness of the thinnest ply. So that's the same requirement as there was for nails. For the spacing between rows of bolts, it's a little bit different. For nails, it was 20 df, if you recall. Yeah, it was 20 df. And for bolts, it's actually 10 df, where df here is now the bolt diameter instead of the nail diameter. Okay, so that one's pretty self-explanatory. And the second requirement, so the second requirement is the same as the third requirement for nails, which is this one up here on the right. So if my h over b is less than 3, then 1 row of bolts is okay. And if h over b is greater than 3, then I'm going to need at least 2 rows of bolts. And that's all the requirements that there are for bolted built-up sections. So as long as I follow those two requirements, the spacing requirement and the number of rows requirement, then I will be able to achieve 75% of my solid weak axis buckling strength for an equivalent solid section. The reason, of course, we don't have the third requirement, or the second requirement that was for nails, the reason we don't have another requirement here is because that one was for penetration and for alternating directions, which obviously don't apply to bolts, since bolts go all the way through all of the members. So that should be all you need to know to design built-up sections with nails or bolts, and we will follow this up with an example problem.